In this short video, we're going to take a look at what we call the tabular method of integration by parts. Right? This is integration by parts, but it's just another method to help us work through some examples like I've got listed below here. X squared sine x, or e to the minus x times x cubed. So some of these examples you'll see as I kind of set things up here. Of course, I would go just like I would regular integration by parts for either of these. I see it x squared multiplied by sine x, something totally different. X cubed multiplied by e to the minus x, something totally different. Different pieces, parts here. So when I use integration by parts, I'll just do one of them. Say u is x squared, du is 2x dx. We'd have to multiply by v, right? Remember that's uv. V I get by taking the antiderivative of sine x. I get a minus cosine x. Then I'm going to subtract the integral of v, that minus cosine again, and my du, 2x dx. Just simplify a little bit. I want to go through this quickly. Minus x squared cosine x plus 2x cosine x. So you'll see here, because of the original function, the fact that I have this power of 2 for my x, and that x squared is what I've taken to be u. I basically have to do integration by parts until I no longer have powers of x in my integral, right? So in that second integral that I have x cosine of x. I have to do integration by parts again, okay? If the power was larger, like in this next example, that x cubed, I'd have to do parts a third time until I'm finally able to say that I've found the antiderivative. So again, we can absolutely do this. But there's a better way. There's absolutely a better way to do this, and it's called the tabular method. Okay? And it's just kind of a nice little way to set up integration by parts when you've got high powers of x that are eventually going to terminate if I take enough derivatives. Okay, so I'm going to set this up using what I call the tabular method. So the way things go is, again, I've got my u and my dv, okay? And I see that u is x squared, dv is sine x dx. I didn't write that on the previous slide, but there it is. And really this left column here, my u column, I'm going to take derivatives all the way down. And my dv column, I'm going to take antiderivatives, right? Because I need v and I need du, okay? So going down, taking derivatives of that u column there, derivative of x squared is a 2x, derivative of that is 2, derivative of 2 is 0, and that's when I can stop. Okay, when that terminates is when I can stop. I do the similar thing with the dv column, but they're not derivatives, they're antiderivatives. Right? So this is just a little tricky. It's very tempting to take derivatives here because that's what we do for the u column, but I need v's. I don't need dv's, I need v's. So when I take antiderivatives here, I get minus cosine x, then a minus sine x, and finally a cosine x. And again, I stop here, and there's my integration by parts formula, and I'm going to show you where all of this comes from. Basically, what this tabular method does is it goes kind of right through the second iteration of integration by parts for us here. It does it basically automatically. Okay, it's got it fleshed out so that the second integral here, this v du, is going to basically integrate that for us right away. The way this works is we're going to multiply down. Before I do that, the minus sign in my integration by parts, that's going to carry through for each iteration of integration by parts that I do. Okay, for each one, that's going to carry through. So the way we compensate for that is by adding a little plus and minus to each one of these guys. Okay, so if I would have had another row, I would have another plus show up in my u column there. Those are going to come in when I write down each of these little antiderivatives here. The first one we have is we multiply diagonally down. And the first one is x squared times minus cosine x. And that's the same as what I got on the previous page, minus x squared cosine x. The next, I would have had to evaluate the integral of 2x times cosine x. Okay? But that would have given me a 2x sine x, what I get by multiplying that second diagonal. Okay? The minus and the minus give me a plus, and I get a 2x sine x. In that second iteration of integration by parts, there's one final integral that I have to do, and it shows up as the integral of sine of x with the 2 multiplied, and that's what I get when I multiply this last diagonal here, 2 cosine x. And of course a plus c. That's it. That's our tabular method. That gives us the entire integral. We can absolutely verify this by finishing what we started with the integration by parts on the previous slide. Yeah. So go back and go through integration by parts again, and you should get exactly this equation here. You should get that antiderivative. I'm going to do the second example. I'll go through it a little quickly and show you the same thing. I've got my u and dv columns. My u's are going to be my x cubes, and my dv's are my e to the minus x's. We typically leave out the dx's here, right? We know those are in there as well. And we take derivatives of the u column, 3x squared, 6x, 6, and 0. Take antiderivatives of the dv column. We have a minus e to the minus x, and that minus sign is going to alternate every time I take an antiderivative. So there we have it. I need my signs on the left side there, plus, minus, plus, minus, plus. Again, that just alternates. And then I'm ready to go, multiplying down. My first term should be minus e to the minus x times x cubed, or minus x cubed e to the minus x. My second term should be that pink minus 3x squared, e to the minus x. The next term, I just keep going until I've gone to where I would hit 0 times the e term, and there's no more terms after that. So what I've got here is a minus 6x e to the minus x. Lastly, minus 6 e to the minus x plus a c. That's it. So something that I would typically have to do integration by parts on 3 times because of this power of 3 for x, I can really just go through, do this derivative and antiderivative column setup, and then multiply diagonally. Now, the tricky part is this only works in kind of some specific situations. Okay? So a quick note, this tabular method doesn't work when the parts change around. In the following scenario, for example, working with an integral of x cubed natural log x. Okay, and we can kind of try to go through it. We would set up our u and our dv column. First, we would think, just as the examples as before, that u would be x cubed. We take some derivatives, no big deal. That means our dv column would start with natural log of x. But then I need integration by parts to even get to that antiderivative. That's going to work. That's not going to work. Same idea as what we ran into when learning integration by parts, right? This natural log in here is actually kind of the opposite method. I would try natural log of x to be my u, but you'll see if we keep taking we can always keep taking derivatives of natural log of x. They don't ever terminate. They don't ever become 0. Same idea by integrating x cubed. We just keep integrating forever. We never stop. Tabular method doesn't work well in these scenarios, right? So for a situation like that, where u would be natural log of x here, I would just go through the regular integration by parts. You shouldn't have to do it multiple times. It should work out just once for that specific example. Right. But that's just a quick video of how the tabular method works. It saves us a lot of time in examples where I've got a high power of x that terminates, and then I'm finding the antiderivative. Thanks for watching.